we were using light as an input to produce electricity. So you can already guess that in electrochemistry, we are using chemical reactions to produce electricity and vice versa, right? We can use electricity to induce a chemical reaction. Yeah? So hence the name electrochemistry. We can use electrical energy to produce a chemical reaction, or we can use a chemical reaction to produce electricity. Because of like these are two opposing processes, this can then lead us to talking about two different types of cells, right? So a cell that we use to produce electricity from chemical energy, we call it a galvanic cell, right? We call it a galvanic cell. And a cell that we use to produce a chemical reaction from electricity, we call it a what do you call this? You guys know it.
Electrolytic.
Electrolytic cell, right? Electrolytic cell. Yeah? And there's only one type of galvanic cell, but we have different types of electrolytic cell, right? So we can do a lot of chemical reactions from electricity, right? And we will talk about them. But before we go into the details, I just want to like remind you of the things you did in grade 10 and 11, which is just simple, basic oxidation and reduction reactions, right? So remember redox reactions from grade 10, redox reactions. So a redox reaction is a reaction that involves the transfer of electrons, right? Meaning that electrons are moving from one substance to another, right? And it's made up of two half reactions, right? The half reaction, it's called the reduction, and the other half reaction, it's called oxidation, right? And you cannot have oxidation without reduction, and you also can't have reduction without oxidation, right? Because of oxidation is the loss of electrons, right? So the electrons that this substance is losing, they need to be gained by another substance, right? And that substance that gains the electrons, because it's gaining negatives, we say that it's reduced. Does that make sense, guys? Remember, what we are transferring here, it's negatives. We are transferring negatives. So whenever we say something has lost negatives, it's going to become more positive, right? So we say that it has been oxidized. Whereas if you gain negatives, you become more negative, then we say that you are reduced. You should make sense of it. So let's take a look at this representation here of a redox reaction. So you would have this substance that has excess electrons or that has more electrons. It loses the two electrons, right? It gives them two Y, right? When X loses these two electrons, it changes from X2 minus to X, right? Because it lost negatives, so its oxidation number must increase. So here, as you can see, its oxidation number here, it was X2 minus, right? It then lost two electrons, its oxidation number became X. If there's no number there, it means there's a zero, right? So its oxidation number changed from a -2 to a 0. So that is an increase in oxidation number, right? So an increase in oxidation number, it's called oxidation, right? It's called oxidation, right? It's an increase in oxidation number, or you can say it's a loss of electrons, right? So the oxidation number increases because of the substance loses electrons. I get, whereas reduction would be the complete opposite. Those electrons that are lost by X would be gained by Y. So Y, its oxidation number would change from a 0 and it would become Y2 minus, right? So as you can see here, the oxidation number, oh, come on, guys, if you're not speaking to us, please mute yourself. So this oxidation number changed from a 0 to a -2. So here we can see a decrease in oxidation number, right? A decrease in oxidation number, right? We call it reduction, or a gain of electrons. Gain of electrons, right? Does this make sense, guys? This is just a revision from grade 11 and 10. Yeah? So now let's pass here. Now, okay, these are the important terms and definitions you need to know. I think we already spoke about them, but we haven't spoke about agents, right? Okay. So a substance that has been oxidized, we call it a reducing agent, right? So remember, when you are an agent, you are an agent to something else, right? So this reducing agent, it's not reducing itself, it's reducing another substance. So when you are reducing another substance, what do? Again, for you to reduce another substance, you must give that substance electrons so that it can be reduced, right? So you reduce that other substance by giving it electrons. But when you give another substance electrons, you yourself are losing those electrons. So we're going to say that you are oxidized, right? So hence, a reducing agent, it's a substance that is undergoing oxidation. The reduction is not happening on the agent itself, but it's happening on another substance, right? And the opposite is true for an oxidizing agent. The oxidation is not happening on the oxidizing agent, but it's happening on the other substance. Do you guys get this concept here, reducing agent versus oxidizing agent? Because it will be very much important as we move forward. All right, let's pass. Right? Yeah? This is, I can see also your hand is up.
I didn't click the button. I don't know why my hand is still. Oh, my bad. My computer just did something just now. It also clicked for some reason.
Okay, no problem. All right, so now let's talk about reactions that are spontaneous, right? Spontaneous versus non-spontaneous reactions, right? So here I would have to introduce the 4B table to you, right? So not all substances are able to react with one another, right? Or are able to donate electrons between one another, right? So it's not always the case that Crazy, please mute yourself. All right. Sorry about that, guys. Ne? So, spontaneous reactions are reactions that just take place on their own without any external pressure, right? Or any external input to make the reaction take place. The reaction I'm talking about here, it's a transfer of electrons. So, if you mix an oxidizing agent and a reducing agent, they would just react with one another spontaneously, right? But then it's not always the case that you mix an oxidizing agent with a reducing agent, then a reaction will take place. It depends on the strength of the oxidizing agent and the reducing agent, whether a reaction is possible between the two. Yeah? So how would you know whether a spontaneous reaction is possible between two substances? Right? Let's go to our 4B table. Right? We will learn about that on the 4B table. So this is the 4B table, guys. Name. There are two tables on your formula sheet. There is a 4A table and a 4B table. I'm gonna teach you how to use the 4B table, and we're gonna stick to this one. Name. So here, guys, this table on the, can you see here the arrows here, the equal signs here, right? So on this side of the table, we have what we call substances that donate electrons, right? Which is reducing agents, right? So as you can see here, the arrow, it's pointing up. It says that the strength of reducing agent increases, right? So the reducing ability on this side, it increases as you go up. So it means that the substances that are on this side of the table, they are reducing agents. Yeah, guys. So they are reducing agents. They donate electrons. Whereas the substances that are on this side, these ones, they are oxidizing agents. They accept electrons, right? So let's say in a container, I mix, let's choose Fe and Na plus, right? In a container, I have Fe solid and Na plus ion, right? Then my question is, will Fe be able to donate its electrons to Na plus, right? How would you know? You would know that from the table, right? So if you take a look at Fe, Fe it's here, right? Fe it's here, Na plus it's here, right? So we say that you cannot donate towards something that is above you, right? So the giver should always be above, right? So as you can see, Fe, it's the giver, right? It's the one that has to donate electrons, but it's below Na plus on the table. Na plus it's up there, Fe it's down there, right? So Fe therefore cannot donate its electrons to Na plus. Do you get that part? Now I'm gonna explain it how you need to explain it in the exam if they ask you. Ne? So because they can give you like a question whereby they put in a metal inside a solution, right? Then they say that there is a color change, or maybe there's no color change. Explain why there's no color change, or explain why there is a color change. You need to explain that by referring to the strengths of reducing agents and oxidizing agents, right? So, how we can do that? Let's take a look at the table again. Yeah? Let's explain this one, right? I'm just gonna teach you how to explain using this one as an example. So you if they say explain using the strength of um, reducing agents, you need to compare things that are on this side of the table, right? So we are going to compare Fe and Na. We compare bananas with bananas, apples with apples, right? So we can't say that Fe has a weaker reducing ability than Na. Sorry, than Na plus. We can't say that. We can't say that Fe has a weaker reducing ability than Na plus. We need to compare things that are on the same side of the table, right? So you're gonna be like, Fe has a weaker reducing ability than Na plus, right? So let's go. Fe has a weaker reducing ability than Na. What this simply means is, it simply means that Na is above Fe on the table, right? So if this is the case, therefore Fe cannot donate, or does not have the enough strength to donate electrons to Na plus, right? Fe cannot donate its electrons to Na plus, right? So if that's the case, if Fe is not donating its electrons to Na plus, what does that mean? It means that Na plus won't be reduced. right? Therefore, a reaction won't take place. If Na plus is not being reduced, therefore Fe also it's not being oxidized. Therefore, a redox reaction or a spontaneous redox reaction won't take place, right? Is it making sense, guys? Please understand this part first. Then electrochemistry moving forward would be easy, right? I can run through it again. So I was saying that it's not always the case whereby you mix substances, then a redox reaction would just take place spontaneously on its own. The reason is it depends on the strength of the substances involved. Is your oxidizing agent, or rather, is your reducing agent strong enough to donate its electrons to the acceptor? Yeah? Is this substance that is on the right strong enough to donate its electrons to the acceptor, right? So if your donator, right, or your giver is below the acceptor, as in the case of Fe and Na plus, Fe won't be able to donate its electrons to Na plus, right? Explain that using the strength of reducing ability. You're gonna say that Fe has a weaker reducing ability than Na. I can't compare the reducing ability of Fe and Na plus because Na plus it's not even a reducing agent. Wouldn't make sense. So I'm gonna compare Fe and Na. So I'm gonna say Fe has a weaker reducing ability than Na. If that's the case, right? If that's the case, if Fe has a weaker reducing ability than Na, it means that Fe cannot donate its electrons to Na plus. It's not fit enough to donate its electrons to Na plus, right? Remember, the ones that are on the right are the ones that accept electrons. So I cannot say that also on this part, I cannot say that it's not fit enough to donate its electrons to Na because Na is not an acceptor. So they would mark you down. So you need to say Fe cannot donate its electrons to Na plus, or it does not have enough strength to donate its electrons to Na plus. If it cannot donate its electrons to Na plus, it means that Na plus won't be reduced, right? Na plus won't be reduced. They want to see this one. This one is a mark. This point is a mark. You need to include it on your answer. Yeah? Then they can still ask us to explain the same thing, but they're now using the strength of oxidizing agents, right? So I can alternatively say that, okay, I'm still answering the same question as to why Fe cannot donate its electrons to Na plus. I'm gonna say that, okay, Na plus or Fe3 plus, Fe3 plus is a weaker, or sorry, it's a stronger, is a stronger, because as you can see on this side, the arrow is facing down, right? So the strongest oxidizing agent is down the table, right? So Fe is a stronger what? Oxidizing agent than than Na plus, right? So this point is equivalent to that point. It's actually telling us the same thing, right? But then now we are comparing, instead of comparing this and that, we are comparing this and that. But these 2 points are actually telling the same story. That is why in the exam, they can say explain using reducing agents or oxidizing agents, right? They can say either or. But then if the examiner is strict, they can just limit you to one option and actually say explain using the reducing agents, or maybe they say explain using oxidizing agents, right? So be aware of that. So this point is equivalent to that one. So if this is the case, it simply means that Fe is below Na plus. You remember, you cannot donate to what's above you, right? So therefore, Fe cannot donate electrons to Na plus. And if this is the case, Na plus won't be reduced. Yeah. So I still explained the same thing, but the difference is the first points are different, but they are all telling the same story. Yeah. But then now, in a case whereby a spontaneous reaction would take place, for example, let me wipe here now. All right. So in a case whereby a redox reaction would take place, let's say we are having Mg and let's say Fe2 plus, right, in a container, right? They mixed them. We have Mg and Fe2 plus and Fe2 plus, right? So we need to compare the donator. How would I know that Mg is a donator? It's on the right hand side of the table, right? I need to compare the donator and the accept. The acceptor is on the left hand side of the table, right? So the donator must always be above the acceptor, guys. It's more of like saying that if you guys are Christians, God is above, then we are here on earth below, right? Only God gives us blessings, right? Blessings, they move from high up there, they go down, right? It's never the opposite. Or you can, let's say, another analogy is that the poor cannot give to the rich, right? So the rich people who are high up there, they give to the poor, right? It can never be vice versa, right? So Mg is above Fe2 plus. It means that it has the ability to donate its electrons to Fe2 plus. But in the exam, guys, they don't want you to explain it how I just gave that analogy that I just gave you. You can't say Mg is above Fe2 plus. It's not allowed. You need to explain using the reducing agents or the oxidizing agent. Let's explain using reducing agents why Mg is fit enough to donate to Fe2 plus. So point number one, Mg is, remember, if I'm using reducing agents, I'm gonna compare Mg with Fe, right? I'm gonna say Mg is a stronger reducing agent than Fe2 plus. Now, if, sorry, not Fe2 plus, Fe. Remember, I'm comparing apples with apples, right? So Mg is a stronger reducing agent than Fe. Therefore, Mg will reduce Fe2 plus to Fe, right? So you must mention that, it reduces it from what to what. Yeah? So it will actually be able to donate its electrons to Fe2 plus, then Fe2 plus would become Fe, right? So that's how the reaction will take place. Yeah? Then if they say we should explain using the oxidizing agents, we're gonna simply come on this side of the table. We will say that Fe2 plus is a stronger oxidizing agent than Mg2 plus. Therefore, we say this thing, the same point. Mg will reduce Fe2 plus to Fe. Oh, all right. then if Mg is reducing Fe2 plus to Fe, what is happening to Mg? Mg will be oxidized to Mg2 plus. So basically, this is how you'd explain this 3-mark or 4-mark question in the exam, right? But then it's very important to form like a foundation as to how uh, galvanic cells work, right? So remember, if uh, the donator is strong enough to donate its electrons, it would happen spontaneously, right? The donation process would happen spontaneously without any extra external force, right, or energy input that we place, right? So it will just happen on its own. This then introduces us to galvanic cells. We are gonna utilize the fact that this one wants to donate electrons to that one to try and manipulate it to create an electric circuit from this, right? So let me just give you the simple idea of a galvanic cell. Right? So here is just an illustration of a spontaneous reaction. So they just placed a zinc metal into a solution that contained copper ions, right? And what they saw here is that a reaction took place, right? The color of the mixture became dimmer. It became dimmer. They also saw accumulation here of metals on the zinc chip, right? So we can explain why this is happening by explaining the redox reaction that is taking place here. If you check Zn, it's our donator of electrons, then Cu2 plus, it's our acceptor, right? So if we go here, you would see that where is the Zn? Zn is here, then Cu2 plus, uh, it's here, right? So you'd notice that our acceptor is below the donator, right? So zinc would be able to give its electrons to Cu2 plus. Then when zinc gives its electrons to Cu2 plus, Cu2 plus would become what? It would become Cu, then zinc would become zinc 2 plus, right? So this is why a reaction, when we just place a zinc metal into this copper solution, it just reacts on its own, right? But then now, because um, we saw that this reaction just takes place on its own, we can therefore try to manipulate it and create an electric circuit. So creating an electric circuit, guys, or producing electricity, you can produce electricity anyhow if you just find a way of making electrons move in a wire. Do you guys get it? If you find a way of making electrons move in a wire, that would produce electricity. So basically, the simplest idea of a galvanic cell here is we're gonna make use of a spontaneous reaction because we know that the substances involved, they wanna give each other electrons. So what would happen if I just take the zinc, the donator, place it here, right? Take the acceptor, place it far away from the donator, right? But still connect them with a wire. They are still connected with a wire. They can still feel each other, right? So this donator of electrons would want to give the electrons to the acceptor. This is Cu2 plus. Would want to give those electrons to the acceptor. But those electrons would have to do what? For them to get to the acceptor, they need to flow through the wire. For the fact that I'm having electrons moving in a wire, that's electricity. That's electricity. I'm producing electricity now. This is the simplest idea or the simplest way in which I can explain the idea behind a galvanic cell. We just want to use the fact that this wants to donate its electrons to that. We use this to create electricity, right? Is it making sense, guys? Or is there any part that you'd like me to no to re-explain? Are we all
Yes,
on the
please
same?
go over explaining the in terms of the oxidizing agents.
All right. So on the table, ne, whether a spontaneous this is like we use this to determine whether a spontaneous reaction will take place or not. Right. So the idea is that on this side of the table we have donators of electrons. These substances, they want to give away electrons, and these ones, they need to accept electrons, right? So if we compare the donator and the acceptor, if the donator is above the acceptor, it means that a reaction will take place. But we can't say that Zn is above Cu2 plus in the exam. That's not allowed. We need to explain using the strength of reducing agents and oxidizing agents. But when I'm going to compare the strength of a reducing agents, I'm going to compare zinc with copper, not zinc with copper 2 plus. I can't compare zinc with copper 2 plus because they are not of the same nature, right? This one, it's a donator. This one, it's an acceptor. We can't compare the two. So I'm going to compare the donator with the acceptor that corresponds, sorry, the donator with the donator that corresponds to this acceptor, right, which is basically Cu, right? So I'm going to compare Zn with Cu. Okay, so if Zn is a stronger reducing agent, as you can see, the arrow is pointing up, right? It's a stronger reducing agent than Cu, right? It means that Zn has the ability to donate its electrons to Cu2 plus, right? So it means that Zn would donate its electrons to Cu2 plus, then Cu2 plus would become Cu, right? But in that process, also Zn, it's also changing as it loses its electrons, it becomes Zn2 plus, right? So that's how you'd explain it. Here I used an example uh, of Mg and Fe, right? So we said that Mg is a stronger reducing agent than Fe, right? So Mg is above Fe, right? So therefore, Mg would be able to donate its electrons to Fe, right? So when it donates electrons to Fe, Fe accepts those electrons, then it becomes Fe, right? So Fe3 plus, it donates those electrons, it becomes Fe, right? But also at the same time, Mg will also change from Mg to Mg2 plus because it's losing electrons, right? And this is how you need to explain it. Let me go to the proper guidelines that are showing how we need to explain that, right? So yeah, here are the proper guidelines, right? Showing how we need to explain. So we need to first identify the stronger if we were explaining in terms of oxidizing or reducing agent, they say we need to identify which one is stronger, right? Either oxidizing or reducing, right? I get it. We're gonna refer to the table. There's no need for us to cram, right? If they want us to explain using reducing agents, we're gonna refer to this side of the table, right? Compare which one is strong. Is it Zn or Cu? You'd find that Cu, it's not there in the mixture, but then uh, we can't compare Zn and Cu2 plus. We need to compare Zn with Cu, right? So just like that, again, we compare which one is a stronger reducing agent or an oxidizing agent. Then identify the species with which it is compared with, right? Which one is weak, right? So you're gonna say Zn is a stronger oxidizing agent than Cu, right? So already that's step one and step two, right? Then state the action, i.e., which species would be reduced or oxidized. So now um, for the fact that Zn is a stronger oxidizing than Cu, now we need to state which species would be oxidized or reduced. Therefore, for the fact that Zn is a stronger reducing agent than Cu, it means that Zn has the ability to donate its electrons to Cu2 plus. Therefore, Zn would donate its electrons to Cu2 plus. Therefore, Cu2 plus would be reduced because I get it. Cu2 plus would be gaining those electrons. Therefore, it would be reduced. Reduced to what? It would be reduced to Cu. That's another mark, right? So these are easy marks, right? State to what species will it be reduced. That's the fact that mentioning that Cu2 plus would be reduced to Cu. Then this is like all the 4 steps, and look at how they answer them, right? Look at this example. They say that can a copper sulfate solution be stored in a zinc container, right? So look, we have a container here. They say that this is a zinc container, it's zinc metal, and the solution that is in here, it's copper sulfate, it's CuSO4, right? So, but remember, CuSO4, it's a solution, so it will dissociate. So we have many Cu2 plus and SO4 minus in here, right? So the substances that are able to react or that would potentially react with one another are Zn and Cu, right? So now let's go. They're just asking us, can Zn donate its electrons to Cu? If Zn donates its electrons to Cu, it means that now the container would be eroding because it's taking part in the reaction with whatever substance is stored in here, right? So it would be a bad idea to store copper sulfate in a zinc container because zinc would react with copper, right? Then therefore the container would erode, right? So can you see how they can ask these questions? But let's see how they answered it. They said that no, right? So now here we are explaining in terms of oxidizing agents, right? So they went to the left-hand side of the table. They went this side. They saw that copper is a stronger oxidizing agent than Zn2 plus, right? Let's go see that point. Copper is a stronger oxidizing agent than what? Than Zn2 plus, already 2 marks out of 4, right? Therefore, because of now copper, it's a stronger oxidizing agent than Zn2 plus. It simply means that copper is below Zn2 plus, therefore copper is below Zn. Therefore, it means that Zn is able to donate its electrons to copper, right? So therefore, Zn will do what? Will reduce copper to uh, copper 2 plus. Because now copper 2 plus is being reduced to copper by what? By Zn. So also Zn would be undergoing oxidation. So therefore Zn would be oxidized to Zn2 plus. Then you get your 4 marks. But let's see how they answered it. Ne? So Cu2 plus is a strong oxidizing agent than Zn2 plus. The first 2 marks, they come from just comparing, guys. Comparing the oxidizing agents involved, right? And will oxidize Zn to Zn2 plus. So they just wanted this point of saying Zn will be converted to Zn2 plus, right? Or you can explain in terms of reducing agents. Zn is a stronger reducing agent than copper. It will reduce copper 2 plus to copper. Oh, now I can see the pattern. I can see the pattern now. So basically, if I'm gonna compare using the oxidizing agents, right? I have to mention whether oxidation will take place or not. So I'm gonna say, okay, copper is a stronger oxidizing agent than Zn2 plus. Therefore, it will oxidize. Look, can you see these two words? They correlate. Can you see them? It's oxidizing agent, oxidize. Reducing agent, reduces. Right? So basically, yeah, this is how you need to be answering it. Ne? This is how you need to be answering it. So let's take another look at this example. Let's take another a look at this second example. It says that it is found that silver does not react with hydrochloric acid solution. Refer to the relative strength of reducing agent to explain this observation, right? So we have what? We have silver, which is a metal, right? So it's a reducing agent. It's Ag with hydrochloric acid. So hydrochloric acid is HCl, but you know that it will dissociate into H plus and Cl minus. So can Ag donate its electrons to H plus. Remember, on these solutions, we are only interested in the positive ions because normally the negative ions, they are just spectators, right? So, right? So now let's go to the table and compare Ag and H plus, right? So if a reaction will take place between the two, so with Ag? Ag is here, right? Then with H plus? H plus is up there, right? So as you can see that Ag is below H plus. So you cannot donate to what's above you, right? So, but we have to explain using oxidizing and reducing agents. So we're gonna say that Ag, if I'm using reducing agents, I'm gonna say that Ag is a weaker reducing agent than H2, right? Therefore, it cannot reduce H plus to H2, right? 4 marks for just saying that. Yeah, 4 marks for just saying that. So we will do more examples and you will get the hang of it, guys. So let's pass this one, right? So yeah, this is the simple idea of how a galvanic cell works, right? So now let's go look at a fully functional galvanic cell, right, with the nitty-gritties of it. So here, a galvanic or a voltaic cell, right? They say that it converts chemical energy to electrical energy, right? So we make use of the fact that this thing wants to donate electrons to this thing. We then separate them, make them far apart, but connect them still with a wire. So therefore, the electrons would need to flow through the wire, right? So electron in the wire, it means that we are here producing electricity. Yeah? So we are making use of a chemical reaction to produce electricity. So we are converting chemical energy to electrical energy, right? So it only happens if there's a spontaneous redox reaction. We cannot produce electricity from a chemical reaction that is not spontaneous, because if the reaction is not spontaneous, even if I connect them, let's say we have Zn and maybe um, Na plus, right? Na plus like that. A spontaneous reaction won't take place, right? Between those two, right? So therefore, I cannot produce electricity from this. Even if I do this, a chemical reaction is not taking place. Therefore, I'm not gonna produce electricity how I want, right? So it works only with spontaneous reactions, right? Remember, spontaneous reaction takes place on its own. So, all right, let's move on then, right? Let's analyze this fully. So, a galvanic cell is made up of two half cells, right? So, in each half cell, you have what we call an electrode, a metal electrode, and its corresponding solution, right? So as you can see, the metal here is Zn. The corresponding solution must contain Zn2 plus ions, right? Then on the other side, our electrode is copper. Then the solution is a copper solution. Please note that in here, we also have some negative ions, right? Like SO4. So this won't be a Zn2 plus solution, but it would be a ZnSO4 SO4 solution, for example, right? There are negative ions as well in there, right? It's very important to understand that we also have negative ions in here to make this solution neutral. Yeah. So just remember that even though we don't show them here, in some cases they are there, right? The negative ions are also there. It's not always the case that the negative ions would be SO4 2 minus. They can also use NO3 and many other negative ions right out there. So what happens here is that it's either the reaction will take place between Z and sorry, would take place between copper and Zn2 plus. Remember, guys, this thing here, it's all electricity. They are all connected. This is an electrolyte. It conducts electricity. This metal, it's a conductor. This is also a conductor, right? So all these substances that are involved here, they can feel each other's energies, right? They are all connected, right? So let's see our donators that are involved. This is a donator. This is also a donator, all right? Our acceptors of electrons that are involved, it's this one and that one. So it's either a reaction would take place between this this donator and this acceptor, or it will take place between this donator and this acceptor. Only one pair would be able to undergo a spontaneous reaction, and you already know why. It's because of their reducing abilities, the reducing strengths. So which pair will be able to undergo a spontaneous reaction? Is it Zn and Cu2 plus, or is it Zn2 plus and Cu? Let's go to the table and compare, right? So if Zn is above Cu on the table, it means that this is a better donator of electrons than copper. So therefore, this one would be the one that donates, right? So let's go to the table and see which one is better. So Zn is here. Where is Cu? Cu is here, right? So Zn is above Cu, right? So it makes that. Can you?
Are you muted?
Am I muted, guys?
It's fine now, sir.
Can you?
All right. So yeah, I was saying that Zn is above Cu, right? So it means that Zn would be the one that donates electrons, right? So let's go there, right? So Zn would donate electrons to Cu2 plus. But then because now they are far apart, the electrons need to flow in the wire, right? And when they flow in the wire, that's a creation of electricity, right? We would see a voltmeter here registering some voltage, meaning that now there is electricity. All right. So now, when Zn donates its electrons, it becomes oxidized, right? So it's gonna change from Zn to Zn2 plus 2 electrons, right? No need for you to memorize these reactions because they are there on the table, right? So Zn, we started with Zn, so it has to move in that direction. So it's gonna become Zn2 plus, giving us 2 electrons. So the one that is undergoing oxidation in a galvanic cell would be the metal that is up there, right? That is at the top because it's the one that it's donating, right? So the donators are up there, right? But then its reaction, we need to write it in reverse, right? We need to write it in reverse like that. All right. So Zn donates its electrons, it becomes Zn2 plus 2 electrons. The Zn2 plus, they fall into the solution, right? Adding into the solution, right? So because now this metal, it's being eaten away, it's eroding. So here we would see what we call a decrease in mass, right? A decrease in mass. Then the electrons, right, they would flow in the circuit like that. Then when they get here, those electrons, when they get here, they would be accepted by Cu2 plus. Remember, electron is negative, Cu2 plus is positive, so Cu2 plus would be attracted to that negative. Therefore, Cu2 plus would gain that electron, right? Those electrons. So when Cu2 plus gains electrons, it becomes Cu solid, right? Because now we are producing a solid metal, we would see that solid metal plastering onto the already existing metal, right? So we would see the Cu metal coating this electrode, right? Because we are producing a metal on the side. So that metal that we are producing, it coats this one here, right? So because this electrode is being coated, it's being coated, we say that, okay, we would have an increase in mass, right? Another mnemonic that I was taught in high school, very important, any electrode that is coated, it's called the cathode. CC. Remember this one. I don't usually teach people mnemonics, don't teach mnemonics, but this one is very important. CC, the cathode is coated. Also, when you go to electrolytic cell, remember that any electrode that is being coated, it's a cathode. Name. So now this reaction would obviously take place, right? Continue taking place. This mass would keep on decreasing. This one would keep on increasing, right? Like that. Yeah? But you'd notice that the neutrality of our solutions would change, right? Remember, we start with neutral solutions, neutral electrolytes. Remember, I told you that in here we also have SO4 2 minus. Also in here we have SO4 2 minus, right? At first, the number of Cu2 plus and SO4 2 minus were equal, therefore creating a neutral solution in here, right? As well as in here, it was neutral. But then now, if you take a look at this one, we keep on pouring more Zn2 plus in here. As this electrode erodes, we keep on pouring more Zn2 plus. It would make this solution to be more positive, and that's not what we want. A galvanic cell operates optimally when these solutions are neutral. All right, so how are we gonna neutralize this positivity? Anyone?
The salt bridge.
The salt bridge, ne? That's correct. So the salt bridge is also made up of a solution. So usually we use potassium nitrate. It's a common solution that is used in a salt bridge. Remember, any solution would dissociate into its uh, components, right? Or its constituents, right? So it would dissociate into K plus and NO3 minus. So basically, in this salt bridge, we have a lot of K plus ions and NO3 minus ions. But because this side it's becoming more positive, the NO3 minus would be attracted to this side, right? So I can see here this is a mistake here they made. So let's ignore that. Okay? So the NO3 minus ions would be attracted into that solution. Then the positive ions, let's explain why they would be attracted into the solution. So basically what would happen is that here, because now remember the Cu2 plus ions that are in here, they keep on accepting electrons here. So the number of Cu2 plus ions is increasing. So it's decreasing. So we would have more of the negative ions than the positive because we keep on losing the positive. So this solution would then become more negative as the cell operates, but we don't want that. That's why we have the salt bridge, which will send positives in here to neutralize the negativity, right? So that's how it actually works. That's how the salt bridge actually works. So in an exam, they might ask you, maybe they would tell you that, okay, the salt bridge is potassium nitrate. Then they would ask you that as the cell operates, are the potassium ions going, maybe they would name this one A, maybe name this one B. They would ask you, are the potassium ions drawn towards A or B? Or maybe ask you, are the NO3 minus drawn towards B or A? If they don't mention what the salt bridge is, they would use the words cation and anion, right? So cation, remember, it's positive, anion, it's negative. So they might ask you, in the salt bridge, where are the anions attracted to A or are they attracted to B? So they might structure that question like that, but it wouldn't make a difference, right? Because you know that the cations are positive, the anions are negative, and you are good to answer it with just that knowledge. So now let's talk about something else, which is called the cell notation, right? So, all right, but before that, we need to find the cell reaction, the overall net redox reaction. So remember what the things that are reacting here is Zn donating its electrons to Cu2 plus, right? So basically, um, to come up with the net reaction, we can use the half reaction. So basically this thing here is called a half reaction. This one here is also called a half reaction, right? So by adding the half reactions, we would get the net reaction. So remember in maths, when you add equations, maybe you have x plus y equals to 4, maybe you have 2x plus 3y equals to 7. So when you add the equations, you're going to add this and that. So we're going to get 3x y plus 3y, we get 4y. Then we say 4 plus 7, right? Then we get something like 11. So the same way we add equations in maths, we're going to add equations here in physics, right? So the arrows, they indicate the equal sign, right? So we have Cu, okay, let's start with the Zn. We have Zn giving us Zn2 plus 2 electrons. Then we also have Cu2 plus 2 electrons giving us Cu, right? So adding the two, Zn plus Cu2 plus. So we're going to have Zn plus Cu2 plus 2 electrons, right? Giving us what's on the left-hand side, what's on the right-hand side, Zn2 plus 2 electrons plus Cu, right? So as you can see, the electrons are on both sides and they're equal. It's more of like having an equation when you have x plus 3y is equals to 4 plus 3y. So the 3y and the 3y would just cancel each other out, right? So also here the electrons would cancel each other out, because if I were to transpose these two electrons to that side, so it would be, when they get this side, there would be 2 electrons minus 2 electrons, which is 0 electrons. So basically that's why they are canceling each other out. I get it. So those electrons, they cancel each other out. Then I would be left with Zn plus Cu2 plus, giving me Zn2 plus Cu. This would be my net equation, as you can see it there, right? Are we all on the same page?
Yes. Yes, sir.
All right. And please note that for metals, Zn is a metal, right? So if it has no charge up there, it means that it's a solid. Then if it has a positive charge like that, it means that it's an aqueous solution, right? Just to clarify this one here, right? Because it will help us when we get here on the cell notation. So the cell notation is just basically taking the galvanic cell and summarizing it into one single statement. Everything that is happening here, we just summarize it into one simple statement. So the cell notation, right, as you can see here, we're gonna start with oxidation, right? Because remember, we always start with the donation, because you cannot have acception of electrons if there is no donation yet. So the donation needs to happen first, right? So that is why we start with the oxidation, right? Half reaction on the cell notation, just to show what happens on the on the anode, right? We need to show what happens on the anode first, right? Just simply saying that we have oxidation first, right? The donation happens before the acception of electrons. So just showing how the Zn, or the reducing agent, changed, right, on the anode side. So Zn changed to Zn2 plus. So this one line here, it represents a change in phase, right? Phase, remember I told you that this is the solid phase, this is the aqueous phase, right? So that's like different phases, right? So Zn was a solid first, then it lost electrons, then it become Zn2 plus, which is an aqueous phase, right? It became it changed from Zn solid to Zn aqueous. So that's what a single arrow represents. A double arrow, it separates the half cells, right? So it means that this is one half cell and this is one half cell. So these two arrows, they separate the half cells. Or we can say that these two arrows are the salt bridge, right? Because the salt bridge also separates the half cells. Yeah? So yeah, we can say that this is the salt bridge, or we can say that this is a separation for the half cells. Then on the other half cell, let's see what happens. We started with Cu2 plus. Remember, on here we just interested on the things that are involved in the redox reaction, really, right? Because remember, it's Zn and Cu2 plus that reacted, right? So we started with Cu2 plus, right? It gained electrons, it changed phase, then it became Cu solid, right? So this is how you write your cell notation. Then also, we also have what we call the standard conditions. These are very important. Write them down. Standard conditions. Don't go in the exam without knowing the standard conditions. Number one, concentration should be at 1 mole per dm cubed. The temperature should be at 25 degrees Celsius. Then if we are gases are involved, then the pressure should be 1 atm. So if they ask you to show your standard conditions on the cell notation, you're just gonna go here. Let's use this one as an example. Remember, our cell notation is Zn, giving us Zn2 plus. Then we have Cu2 plus, giving us Cu. If we were asked to show our standard conditions on the cell notation, remember, concentration only applies to what? It only applies to substances that are in aqueous solution. So this substance, it has concentration. So I'm going to show that its concentration is 1 mole per dm cubed. Also, this substance also has concentration. Its concentration is 1 mole per dm cubed. But if you go on to say that the concentration of Zn, which is a solid, is 1 mole per dm cubed, they're going to mark you down because Zn does not have concentration. It's a solid. We did this also in chemical equilibrium. We know that solids, they don't have concentration, just like liquids, all right? So, but the temperature applies to everything. So I can just say here, right, temperature equals to 25 degrees, right? Just to show that it applies to everything, right? There are no gases, so I can't talk about pressure. Remember, pressure, we only talk about pressure in gases, right? So I can't write that the pressure is 1 atm. The pressure of what? Which is not here, right? So I can't include that one. Name. So, and you can also notice that on the cell notation, the outer borders are my electrodes, right? So this outer border is my cathode. This one is my anode, right? Also, it's also in alphabetical order. If you're gonna look at it that way, we start with the anode this side, then we end with the cathode on that side. I think I covered almost everything on galvanic cell. Then the remaining thing is the cell potential, right? So the cell potential is basically saying calculating the voltage here, the initial voltage here under standard conditions, right? So E cell, would you just take the E of the cathode cell, then E of the anode cell, minus them, right? So the values, you'd get them on your table, right? So they are on this table. This table of mine does not show those values, but in your exam, the values would be here, right? So the values would be here and the formula is just here, right? It's also there on your formula sheet. You can just use the formula to calculate E cell. But then one important thing about the E cell, they can ask you to calculate, then interpret. Yeah. So let me add a page here. They can say calculate E cell and interpret that value. So A positive E cell, it means that the reaction is spontaneous if the E cell is positive. Then if it's negative, then the reaction would be non-spontaneous. That's like some other important details you need to know. All right, so let's pass this one. Now, we also need to talk about the factors that influence the value of the E cell. So these ones are very important, especially for those explain question for 1 mark, 2 mark, right? So we have that the nature of the substances that are involved, right? So if we have strong reducing agent and a strong oxidizing agent involved, then the E cell would be much higher. So what does that mean? It means that if you, let's say I have a galvanic cell where my substances that are reacting are Zn and copper. And on another galvanic cell, I have Mg and copper steel and copper 2 plus steel, right? So the first galvanic cell, the purple one, this one, its cell potential would be less than the one where I use magnesium and copper. Because now on the one where I use magnesium, as you can see, I used a stronger reducing agent, right? Or you can look at it this way. If the substances are further apart on the 4B table, then the E cell would be much higher. So if we take look at the first cell, you see the length between them. Look at this one here, which is just like a shorter distance between the substances. So the substances with a longer distance, the cell with a longer distance between the substances would have a bigger E cell, right? So the E cell would be larger if I use Mg and Cu2 plus. The reasoning behind would be that Mg is a stronger reducing agent than Zn. Yeah, so that's how you'd explain it. So that's point number one, right? Or what else can influence the cell potential? It's the concentration of the reactants and products, right? So you'd read this name, but what I just want to tell you is that a galvanic cell, there is a reaction that is actually reversible, right? It's a reversible reaction that is taking place here. Yeah? So the forward reaction would be moving electrons. Let's take this one as an example. The forward reaction would be moving the electrons in that direction, right? And the reverse reaction would be moving the electrons in that direction. So now, remember, like in chemical equilibrium, we always start with the forward reaction. So as the forward reaction takes place, its rate decreases, then the rate of the reverse reaction keeps on increasing, right? So as the rate of the reverse reaction keeps on increasing, it means that now electrons starts to want to flow in that direction more. But then the rate of the forward reaction is still faster than the rate of the reverse, right? But it still overpowers the reverse reaction. So therefore, the overall flow of electrons will be in that direction till a point whereby now the rate of the reverse reaction would be equal to the rate of the forward. Remember, the rate graph would look like this. Um, we would have that the forward reaction, oh, that's the reverse, and the forward reaction would look like this, right? So this is the forward, right? And this is the reverse, right? So as you can see that as the forward reaction takes place, its rate decreases, but of the reverse, it increases and increases till we reach equilibrium, right? So when we reach equilibrium, at this point, the rate of the forward reaction is equal to the rate of reverse reaction. So the rate of flow of electrons in that direction would be equal to the rate of flow of electrons in that direction, which makes the flow to be zero. Therefore, there is no longer a net flow of electrons. It's as if there is no longer a flow of electrons Therefore, the voltmeter reading registers as 0. But it does not mean that the reaction has stopped. The reaction does not stop. It just reached equilibrium, right? That is why even in a battery at home, if you have a battery, remember this galvanic cell is a battery, right? Even if you have a battery, when the battery is flat, it doesn't mean that the chemicals within the battery have been depleted. The chemicals are still there. That's why, because me, I used to bite them. When you bite the battery, even if it's flat, you'd still feel the chemicals inside the battery, right? So don't try this at home. Don't go bite batteries just to confirm. So yeah, the chemicals are still there. It's just that the reaction, right? The reaction has then reached equilibrium. So now, to increase the V, remember when I'm saying that the reaction has reached equilibrium, I'm talking about the overall cell reaction, right? Which is Cu2 plus Zn, giving us Zn2 plus Cu, right? So when I say that it has reached equilibrium, basically I'm saying this reaction because it's the net reaction, right? So now the forward reaction and the reverse reaction, their rate are equal. So if I increase the forward reaction, right, which is basically the reaction between Zn and Cu2 plus. Yeah, guys, the forward reaction is the reaction between Zn and Cu2 plus. So the reaction between these two, it means the electrons are flowing in that direction, right, which is the original direction, right? So if I increase the forward reaction or whatever change that I make such that I increase the forward reaction, it will increase the current. It will increase the flow of electrons. It will increase the value here, right? So I'm not gonna say any more details here. I'm just gonna say any change in concentration that favors the forward reaction will increase the cell potential. The opposite is true. Any change that decreases the rate of the forward reaction would decrease the cell potential, or any change that favors the reverse reaction would decrease the cell potential. Are we all on the same page, guys?
Can you explain the case, please?
All right. The thing that I'm explaining here, it usually comes as a 1-mark question, right? Where they just want to see if you understand. So the net cell equation, it's an equilibrium equation, right? So what is our forward reaction? Remember, our forward reaction is the spontaneous reaction where Zn reacts with Cu2 plus. So as you can see, our reactants are Zn and Cu2 plus. These are our reactants. So this is the forward reaction. But in the forward reaction, the electrons flow like that, right? The electrons flow like that, right? So if I favor the forward reaction, I'm gonna increase the value here. But if I favor the reverse reaction, which is basically this direction, I'm gonna decrease this value here. How can I favor the forward reaction in this case? Maybe if I add Cu2 plus, right, come into this container, add more Cu2 plus, right, it will therefore favor the forward reaction. Or I can maybe remove Zn2 plus from this container, decrease the concentration of Zn2 plus. So it means that I decreased this. So to increase it, the reaction would favor the forward, right? So when the forward is favored, it's gonna increase the cell potential. Guys, I don't want you to cram a lot of things. Just say any change in concentration. Remember, concentration only applies to Cu2 plus and Zn2 plus, right? Any change in concentration that favors the forward reaction will increase E cell. Then you're good to go. I, you are good to go, because of in the exam they might just decrease this. They say that, okay, on this cell we decrease the concentration of Cu2 plus. What effect will this have on the E cell? Decrease, increase, or remain the same? The first thing that you need to answer would be, would a decrease in this favor the reverse or the forward reaction? You already know that it will favor the reverse. So with the reverse being favored, this value would decrease. That's all. That's all, guys. Let's not complicate it. Ne? So I'm gonna pass this one. All right. So the explanation process, yeah, we are done. All right. So this is just explaining what we were explaining. Then we are done with galvanic cells, guys. Let's go. Should we do questions on galvanic cells? Let's. I think, should we do questions on galvanic cells, or should we then go do photo bargaining electrolytic cells?
Galvanic cell, please.
All right. So I'm gonna give you time. Let me give you like 10 minutes to do this one. Okay, but 10 minutes is a lot. Let's keep it at 7. Oh, I think I have a video on electrolytic cells. I'm just gonna check it though. Um, okay, guys, are you done? Hello. Yeah, but what we did? Let's correct this question. All right. So here we are given that a learner conducts two experiments to investigate the reaction between copper and silver nitrate solution. Right. So here's the first experiment. The learner adds a small amount of copper powder, right, into a test tube containing silver nitrate solution. The solution changes from colorless to blue. All right, there was a reaction taking place here. Changes from colorless to blue. So a color change means that a reaction took place, right? And the learner just mixed the substances and spontaneously the reaction took place. So they want us to explain why the solution turns blue, or explain why there's a spontaneous reaction by referring to the relative strength of oxidizing agents. Look, here they were specific. Use the strength of oxidizing agent. 4 marks, right? How would you guys explain this one? I'm expecting this one to be an easy one, right? So here we have copper, right? Metal, which is a solid. Then we have AgNO3. Remember, AgNO3 would separate into Ag plus and one and NO3 minus. So we are interested in the positive ion and the metal. The negative one is just the spectator, right? So, Ariane, guys, explain now why a reaction takes place between copper and Ag plus by referring to the table. You can zoom it in so that you can use it.
So
We
can
have
I try?
copper, yes, and
Uh,
Ag.
Ag is a stronger oxidizing agent than Cu.
Okay,
Therefore,
wait. Ag, Ag is this side. It's not even an oxidizing agent. Can you see? Ag,
Ag plus.
yes, you should be specific and say Ag plus, né? Because if you don't, you're gonna lose marks.
Okay.
Ag plus is a stronger
Oxidizing agent than Cu2 plus.
agent than Cu2 plus. How many marks do you think you would get for just this?
For my two.
2 marks, right? For just that statement,
One.
2 marks. Ag is a stronger oxidizing agent than Cu2 plus. You saw how they mark it, right? From this one here. Where is it? Cu is a stronger oxidizing agent than, right? That's 2 marks on its own. Then yeah, let's move on.
Therefore, Ag, Ag will oxidize Ag plus.
No, Ag plus will oxidize Cu. Remember, the
Oh,
reaction will be between Ag plus and Cu, right? So Ag plus will oxidize Cu. What does it mean when I say Ag plus would oxidize Cu to what? It will oxidize it to what? What will
To
Cu,
Cu2 plus.
Cu,
Cu2
Cu2
plus.
plus.
Cu2 plus, right? What does this statement mean in terms of um, electron transfer?
So can I try?
Yes.
So since Ag plus will oxidize Cu2 plus, that means that Ag plus is the um giver of electrons, and then the Cu2 will accept the electrons.
Mm-mm. No, it's incorrect. The giver is Cu, the acceptor is Ag plus. That won't change. Ag plus oxidizes Cu2 plus. What is to oxidize, guys? This is the first thing that we learned in the beginning of the session. Hmm? What is to oxidize? They say that Ag plus will oxidize Cu. When Ag is oxidizing something, it means that it's an oxidizing agent, right? So it's causing Cu to be oxidized. For me to oxidize to oxidize something, you need to take away its electrons. So it means that Ag plus is taking Cu2 plus's electrons. Then Cu2 plus will become, sorry, Ag plus is taking Cu's electrons, then Cu would become Cu2 plus. That's what this statement means. Remember, to oxidize is to lose electrons. But when I'm saying Ag is oxidizing Cu, it means that Ag is taking electrons from Cu. This is the first thing we learned at the beginning of the session. Right? So, yeah, that's how you'd explain it. Then the blue color, basically the blue color comes from Cu2 plus ions, right? So Cu2 plus is blue, right? It makes a solution to be blue in color. So all the colors, guys, they are due to the positive ions, right? So most solutions, they have their color because of their positive ions, right? But the blue one, the fact that copper 2 plus ions are blue, this one is a must to know, guys. I'm not expecting you to know others, but let's say that they say that the solution turned green or something. Just think of the positive ions. Yeah? The positive ions are what cause the colors, right? So yeah, that's how you'd explain that one. You see, guys, galvanic cells that are divided into two, right? So the first question would be just like you trying to understand spontaneous reaction. Then the second part of the question would be the cell itself, right? So because now, as you can see on this experiment, they established that the reaction between Cu and Ag plus is spontaneous. Then they use Cu and Ag plus to set up a galvanic cell. As you can see here, they used Ag plus and Cu to set up a galvanic cell. Okay, so now they say on question 2.3, write down the energy conversion that takes place in a galvanic cell. Energy is converted from what to what?
Chemical to electrical.
Chemical to electrical energy.
To electrical. Then 2.4, which direction will N ions, right? N ions are the negative ones, right? Move in the salt bridge. Are these ones N ions or these ones are N ions? So what's your answer?
I said A
Why? How did you get to that conclusion?
because silver is oxidized, it loses electrons.
All right. So silver. Let's just write down what happens here, right? So you said that silver is the one that will be oxidized.
Yes,
Oh, that's not true, because if I come here, I see that Cu is above silver. So how is it that Cu now is not the one that is being oxidized? Cu is the one that has to lose electrons, right? Because it's above Ag. Okay, so let's go here. Cu needs to lose its electrons. So it loses electrons. The electrons, they flow in the wire, but as it loses electrons, remember, the Cu2 plus ions would fall into that mixture, right? So when Cu2 plus fall into this mixture, what happens? It becomes more positives. Then if it's more positive, it's gonna attract what? It's gonna attract the negatives that are in here. So A has to be negative. Is it making sense, guys?
No, sir. Please explain again.
We went to our table, right? Let's look at our substances that are involved in this galvanic cell. We have Cu, right? This is a donator of electrons. We have Ag, which also is a donator, right? We have Ag plus, which is an acceptor. Cu2 plus is an acceptor. But a reaction needs to take place between one pair, guys, one pair of an acceptor and a donator, right? So our acceptors are on the left side, are this side of the table. The donators are this side of the table. Guys, this thing is straightforward. Donators are here, acceptors are here. Then if you want to change it, Minang SARS. So we have two donators this time. We have Cu2 plus and Ag. The stronger one needs to win. Which one is stronger? As you can see, the arrow is facing up. As you go up, the strength of being a donator increases. So the Cu would be the one that would donate electrons, right? Then with that being the case, it means that Ag plus would accept those electrons, because also if you look at Cu2 plus and Ag plus, it's a better acceptor than Cu2 plus. So Ag plus would accept those electrons, not Cu2 plus. So the reaction would take place between Cu and Ag plus. But the electrons, in order to move from Cu to Ag plus, they need to flow through this wire. They need to flow through this wire, right? But remember, we said that Cu, it loses electrons. When it loses electrons, it moves from Cu to being Cu2 plus. Remember, it's a change in phase. Cu is a solid, Cu2 plus is an aqueous solution, which is something that is dissolvable in water, right? So that Cu2 plus would then fall into the water, right? It then falls into the water. So it means that this thing here, it's eroding. Again, but then because now I'm introducing more positives into the solution, it makes this solution to be more positive because more positives are falling into the solution, right? It makes it more positive. So if it's more positive, remember, we want it to remain neutral at all times, right? Because remember, we are just showing Cu2 plus here, but then there are also some negative ions, spectator negative ions. Maybe I can say SO4 2 minus, they're also there. At the start, I have equal number of SO4 minus and Cu2 plus. But because now, as the reaction takes place, Cu2 plus pours into the mixture, it becomes more positive. So if it's more positive, to neutralize this positivity, the salt bridge will send negatives in here to neutralize that positivity. That is why A has to be negative, then B has to be positive ions that are going into this one, right? So our answer for 2.4 would be B, right? So now let's move on to 2.5. Yeah? Are we all? Yes. Yeah?
One thing that we were told about looking at the table is that the thing that's on top will always undergo oxidation, and the one underneath always reduction. And
Yes,
electrons flow from anode to cathode.
yes.
So then electrons will flow from A to B.
So I saying 2.4 is what I think.
Yeah, yes, it's B, sir. So because at Cu it will be the anode, so then electrons will flow from A to B.
Mm-mm. Uh, okay, yeah, electrons would flow from A to B. Remember, A to B has nothing to do with electrons. A and B are actual like solutions. Like maybe it can be potassium nitrate. Let's say, for example, as a salt bridge, they used potassium and NO3 minus in the salt bridge. So in this case, if they use potassium nitrate, A would actually be NO3 minus ions, NO3 minus, and B would be potassium. These are not electrons. I don't know where the electrons come from.
Oh, okay, so I see, sorry. It was just my wording that was incorrect.
Oh, all right, no problem. But do you get it, right?
Yes, sir.
I don't get it.
Okay, which part is confusing you?
The direction that uh, the anions are moving. Because there aren't anions negative. Like,
They
so I
are.
don't know.
Okay,
Uh,
all right. Jehovah, to which language do you speak?
It's why
All right. Bona Jehovah, zone. Moki, name. Solution is a Thomas positive, neutral. Why you see when we say something is neutral, unmute yourself so that we can discuss. Do you understand when we say something is neutral? Do you know what that means?
yeah.
Yeah,
Yes, sir.
right. So in this beaker here, this one, retomarinale, the Cu2 plus, the negative setting, they are not showing them here, but they are
Mm,
there because the spectator they are there. The negative ion setting, maybe the SO4 2 minus, right?
mm,
Right. More this
yes.
electrode, more this electrode, yeah, copper. What's happening here? You tell me what's happening here on this copper electrode.
Copper is being oxidized.
What does that mean? It means
It
that
means it's
it's losing electrons. I get
yes.
whenever it loses electrons, it's gonna change phase, right? It's gonna change from being a metal. As you can see, this is a metal, right? It's gonna change
Yes.
from being a metal to being an ion, to being an ion. Let me represent an ion like that. So as it loses electrons, the electrons would flow up into the wire, right? But then the
Mm,
Cu2 plus, they would fall into this mixture. Again,
yes.
so you would have more of the Cu2 plus ions which are positive falling into the mixture. Now our solution that was neutral will no longer be neutral. It will be a charge area.
Wait, so
If
please repeat.
remember at first I told you that this solution was
It's
neutral before the
neutral.
reaction, right? It was neutral
Yes.
before the reaction. But as the reaction
Yeah.
takes place, you agree that Cu2 plus would fall into this mixture, right?
Yes, making the solution more positive.
More positive, but we don't want it to be more positive. What can I do to
Mm.
neutralize that positivity?
You can bring the negative, the anions in it.
Where will the negatives come from? The salt
From
bridge.
yes. Oh.
Whatever. So the
Yeah.
salt bridge is bringing in the negatives to neutralize that positivity caused by the reaction. So basically, that's what is happening.
Mm.
So the opposite would be
Okay.
true. The opposite would be true on this side. Remember, on this side, we started with the same as the before the reaction starts. we start with the same number of positives and the same number of negatives. I get so, but then as the reaction takes place here, we said that Ag plus is being reduced. I get so this Ag plus, it gains an electron. When it gains an electron, it becomes what? Ag,
More
which is
negative.
solid,
Oh, yeah.
right? Which is solid, right? So remember, Ag plus is dissolved in the water, right? Then, but then now, when it becomes Ag, it's gonna go out of the water and go stick into the into the metal there, right? So basically, it's like we are removing it from the solution. So at first, my solution was neutral. Then I removed positives. By removing positives, what will be the new charge?
Negative.
Negative. To neutralize that negativity, what should I do? Because I don't want it to be negative, right? I want it to be neutral. The salt bridge needs to bring in positives. So in this case, the positives, if maybe they used a solution of, or on the salt bridge, maybe they used potassium nitrate, my positives would be potassium. But in this case, B would be my positive, right? So B would be going in that direction. Oh, now I see why the answer here is wrong. Maybe that's why you were questioning it, ne? Because now we
Yeah,
said that the negative. All right, yes. So I wrote the opposite of what I'm saying. So this is A, actually.
Okay, thank you, sir. I understand.
All right. Now let's move on to 2.5. Calculate the EMF of this cell under standard condition, right? All right, I think I don't have the table with numbers. Can you guys send it to me? Oh, okay, let me just get it on my examination guideline. Now here's the table with numbers. All right, this is for B. Ne? Kana re berekisa AG le yo, ke dirang bjana? So kana here we are using AG le copper. Ne? Let me just go here. AG is here. Copper 2 plus is the copper here, right? So our E cell, remember I remove the formula sheet. The formula sheet here. This formula sheet here, the E cell is equals to E reduction minus E oxidation, or E cathode minus E anode. Guys, here you can use this to cram. In a galvanic cell, the cathode, at the cathode, reduction is taking place. At the anode, oxidation is taking place. Because they need to be corresponding, right? So we can go back to our table so that we can calculate E cell, right? So here it's where oxidation is taking place, here reduction is taking place. So E cell is equals to E cathode minus E anode, right? Just copy the formula. So which one is our cathode? The one that is being coated. Can go back here just to see. It's this one, right? Because Ag accepts electrons, it becomes Ag solid, which is becoming coated here. So we're gonna take this value of 0.80 minus 0.34 and put that in our calculator. 0.8 minus 0.34, which is 0.46. V. Yeah? So this would be your E cell for this reaction. Then you just get your 4 marks or just doing it. Yeah? So write down the balanced equation for the net cell reaction that takes place. So how is your net cell reaction, guys? 2.6. So remember, we need to take the half reactions and add them, right? So I can start with the oxidation half. So the oxidation was taking place where? Here, right? Cu was losing electrons to become Cu2 plus. So I have Cu2 plus 2 electrons giving me, no, I'm lying, Cu2 plus giving me, Cu giving me Cu2 plus 2 electrons. Then my reduction half, I have Ag plus gaining an electron, then becoming Ag, right? Can go here, you can see them, right? The equations. So the one that is on top of the reaction, we need to write it in reverse, remember, right? So that is why we have Cu giving us Cu2 plus 2 electrons. The one on top, we write the one at the bottom, we write it like forward reaction. So it's gonna be Ag plus an electron giving us Ag. If you want to make use of the form of the table, then before we do anything, we need to make sure that our electrons are balanced. Yeah? So as you can see here, the electrons are not balanced. So here there are 2 electrons, then on this reaction there is only 1 electron. So to balance them, I can multiply this equation by 2. So multiply this by 2, multiply this by 2, multiply that by 2 as well. So now the electrons are balanced. So now for the net equation, I can then now start adding the substances after the electrons are balanced. So I will have Cu plus 2Ag. So I already know that the electrons would cancel each other out. No need for me to add them. So then I would have Cu2 plus here plus 2Ag plus. Wait, Ag plus again. Ag plus more than Ag. Are we all on the same page, guys, with this one? All right. Now let's take a look at 2.7. It's that question now, that interesting one. How will the addition of 100 centimeter cubed of 1 mole per dm cubed silver nitrate solution to the silver half cell? So here we add 1 mole per dm cubed Ag plus. Basically, we add more Ag plus in here. Oh, but it does not change the concentration because I still added the same concentration, but I just added more of the substance, but the concentration is still the same. So there's no, if you think about it, there's no change in concentration. So the concentration of silver nitrate will still be the same, right? So this then won't affect the cell reading. That's my thinking around it. So it will be remain the same. Do you guys get it? Because remember, it's our sorry, to see the effect of concentration on the EMF, right? We need to take a look at the overall cell reaction, right? So if I add or if I increase the concentration, if I increase the concentration of Ag, right? I'm saying if I increase the concentration of Ag, then it means that the forward reaction would be favored. But then look, guys, now I did not increase the concentration of Ag. I added Ag still of 1 mole per dm cube. Whereas even at the first, it was still 1 mole per dm cubed. So me adding more 1 mole per dm cubed does not change the concentration. So the concentration of Ag plus remains unchanged. Therefore, doesn't affect the EMF, right? As long as I did not tamper with the concentration, then it's still going to be the same. I only just, if you think about it, I only just increased the volume, but the concentration is still 1. Do you guys get it?
Yes.
Yes, sir.
Okay, then let's pass. Okay, this was from 2024. You guys go do these questions on your own. Then try to answer them on your own. Then after that, go watch the video. Yeah, I'm gonna post 2 videos. I'm gonna post this video of today's session, and the other video would be on electrolytic cell. It's a session that I've already had, so go watch it. Yeah, so that uh when we meet, we can then push other topics. Let's not focus on one thing, right? Yeah, because Ndumiso won't be with us anymore. So we need to make use of the little time that we have together wisely. Yeah. But yeah, as you can see, guys, the questions are really not difficult. We can just run through this one fast just to see what they usually ask. Yeah. So here you see that they say that dilute hydrochloric acid reacts with magnesium at 25 degrees, right, according to the following balanced equation, right? So use oxidation numbers of each of the reactants and explain why this is a redox reaction. So this is basically grade 10 work, right? So even though I didn't like teach you this in grade 12, but from grade 10 and 11, you know how to do this, right? Because you know that the oxidation number of Mg is 0 because it's a compound, right? It's a neutral compound, so it's a neutral element. Then every time the oxidation number of H it's positive 1. So because of Cl is bonded to H, they bonded at a 1:1 ratio. So Cl would be minus, right? So they neutralize each other. Then we know that Cl is minus, so Mg would be 2 plus, then Cl is still minus here, then H is 0, right? So you can see that the oxidation number of Mg, it changed from 0 to Mg2 plus. So its oxidation number increased, so oxidation took place here on Mg, then H, um, its oxidation number decreased from positive to a 0. So reduction took place here. So you're going to be like, okay, the oxidation number of Mg changed from 0 to 2 plus. The oxidation number of H changed from plus to 0. Therefore, this is a redox reaction because there is a change in oxidation numbers. Then you go to 8.1.2, write down the formula of the oxidizing agent in this reaction. So the oxidizing agent is the one that has been reduced. Which one has been reduced? H plus was reduced. So we're going to be like H plus is the one that is reduced, right? So let's move on. It is observed that dilute hydrochloric acid does not react with copper at 25 degrees, right? Explain this observation by referring to the relative strength of reducing agents. You see, in 2024, they said they should explain using reducing agents. I'm telling you guys, there's no way that this question where you need to explain using either oxidizing or reducing agent won't be there. It will always be there. So attempt it. So use your 4B table. While dilute nitric acid reacts with copper at 25, will dilute nitric acid react with copper at 25 degrees? Choose yes for no. Explain in terms of the relative strength of oxidizing agent. Look at this, guys. 2 plus 3 marks, all just explaining using relative strength of reducing or oxidizing agent. 5 marks. It's always there. This question will always be there. They will just try to bring it in different ways, but it will always be there. So please make it a point that you are able to explain. Then after this, you see this is the first part of the question. Then once you are done with it, they then take you to the actual galvanic cell, right? But here the galvanic cell was given to us as a as a cell notation, but the metals that are involved here are Pb and Pt. All right, I like this one because we have platinum which is inert. So it just acts as a surface for the reaction to take place. It's not really involved in the reaction. So let's talk about it now. So how this galvanic cell would look like is that I would have a half cell here, another half cell here, and I have this metal. That metal, it's in a solution. It's also in a solution. Then I would also have a salt bridge, and these ones are connected like that, right? So this is my galvanic cell. So this is Pb here. This one is platinum here. Remember, I told you that the outer borders are your electrodes, right? So my first electrode is Pb, my other electrode is Pt. So here it's where oxidation is taking place, right? So they're telling me that Pb changed phase to Pb2 plus, so it lost electrons, right? So to become Pb2 plus, so the electrons would flow in this direction, right? So Pb would lose electrons to become Pb2 plus, so the Pb2 plus would fall into the solution, right? It will fall into the solution. Then on the other hand, what is happening? We have Fe3 plus donating an electron to become Fe2 plus. Both Fe3 plus and Fe2 plus are aqueous. So this thing is just still happening inside of the fluid. Fe3 plus loses an electron to become Fe2 plus, right? So this thing, all this thing here is just happening inside of the barricade of the liquid. Oh, actually, it happens on the platinum, right? So remember, the electrons when they get here, they would be on the platinum metal, right? Then the platinum metal would then transfer those electrons into the solution so that Fe3 plus can gain them. Then once Fe3 plus gains that electron, it becomes Fe2 plus, right? So the bottom line is that they are all Fe2 plus and Fe3 plus, they are all dissolved still in the solution, and there won't be any coating of this metal. It won't be coated, right? It won't be coated. Yeah, so we won't see any coating of this metal. And this side becomes more positive, right? Because positives are falling into the solution, it becomes more positive. So the salt bridge is gonna send negatives there, right? I think I've put in enough information here. Let's just answer the questions. Yes, Chofad.
So I wanted to know why we use PT because I thought we only use it if we're doing for gases, if we're writing cell notation for gases.
Why are we using PT here? It is also
Yes.
possible to use it if it's not gases, because of look, when Fe3 plus changes to Fe2 plus, these things here, they will still remain aqueous, right? So the PT is just acting as a surface for the reaction to take place. I don't know who told you, Hore, they only use it in if there's gases, but it does work also if these elements here would remain aqueous, both of them,
Mm, okay.
right? Yeah, it does work also like this. It's not always the case that PT, we only use it if it's a gas, right?
Yes,
Yeah.
thank you.
All right. Um, the question says that a stronger reducing agent is now used with the same oxidizing agent. Remember on our notes, they said that if we use a stronger reducing agent or oxidizing agent, the E cell would increase. Again, guys, they said that it would increase. We spoke about it. We said that if we use a stronger reducing agent or oxidizing agent, then the E cell would increase. So increase, sure. And they don't even want you to explain it. This was all on galvanic cells in 2024. Let's see 2023. Guys, can you see the pattern? I think you can already see the pattern. The first part of the question is this one where they want you to explain using oxidation numbers or using oxidation strength or reducing ability. Explain here. Then you come here to the actual galvanic cell. Ikalapalla, guys. Ikalapalla, guys. Please make it a point. Now, my only concern, I know that the galvanic cell itself is much easier, but please make it a point that you practice this, be able to explain this, because here there is a lot of marks, free marks here, right? So, but let's take a look at it. They say that silver nitrate is mixed inside a solution with copper strip, right? So we know that, okay, this is a copper metal, right? So when we go to our 4B table, we see that copper is above Ag plus. Remember, this one would dissociate actually into Ag plus and NO3, NO3 minus. All right, then I give it a little bit. I get black. NO3 minus like that. Yeah? So we are interested in the metal and the ion, right? So the question is the metal able to donate its electrons to the ion, right? That's the question we want to answer. So we can already see that, okay, copper is already above Ag plus, right? So the reaction is possible here, right? A spontaneous reaction is possible. So let's see again. If a spontaneous reaction would take place, basically it would be copper donating its electrons to Ag, right? So when copper donates its electrons, it becomes copper 2 plus 2 electrons, right? Then Ag accepts those electrons, it becomes changes from Ag plus, it becomes Ag solid, right? By accepting an electron, right? So to answer the question here, name one observation beside the solution turning blue. We know that the solution is turning blue because as copper loses electrons, it becomes copper 2 plus, which is blue in color. Remember, I told you that you should know that copper 2 plus is blue in color. This one is a must know, right? So, but then what other observation would we see? We would see deposits of would okay, this is not Ag plus, it's Ag solid, right? So Ag plus, which was in aqueous solution, is gonna become Ag solid, right? So we would therefore see deposits of Ag solid on the floor there, right? We would see deposits of Ag solid on the floor. Is it making sense, guys? Because of now, it will change. It will change our face from it's this one. It's actually here. Let's go back here. Can you see what happened here when they reacted? Um, when they reacted zinc with copper solution. So you see, we also saw like some deposits on the floor there, right? So we saw like some deposits on the floor of the solution. So the same thing is happening in this case. So we would see some deposits here, deposits of Ag, right? The Ag solid. So name two, okay, so the name of the formula or oxidizing agent. So the oxidizing agent, the one that is reduced, which one gained electrons? Ag plus. So Ag plus gained electrons. Explain the answer to 8.1.1 by referring to the relative strength of the oxidizing agent, right? Explain why we see the deposition of Ag. How does this Ag come about? So we're gonna compare. They said we should use the relative strength of what? Oxidizing or reducing agent. So here they are not limiting it. So basically here you need to explain why is there a production of Ag plus. Either you can use oxidizing agents or reducing agents. It's up to you, right? Let's do it together. So here we can already see that, okay, let's use reducing agents, right? So I'm gonna compare Cu and Ag, right? Bananas with bananas. Cu is a stronger reducing agent than Ag, right? Therefore, Cu will reduce. Again, what will Cu reduce? It will reduce Ag plus because it will donate its electrons to Ag plus. Cu will reduce Ag plus to what? To Ag. You are done. You get your 3 marks. It's simple, guys. This question. Again,
Yes.
now let's look at the galvanic cell itself. Here we are given that a galvanic cell is set up using copper and Ag. They established using this reaction that, okay, a spontaneous reaction takes place between Ag plus and copper. So we can set up a galvanic cell using the two, right? Then they set up a galvanic cell, right? So before you set up a galvanic cell between two substances, you need to know that a spontaneous reaction will take place, right? So without a spontaneous reaction, then there's no galvanic cell. All right. So here is A, here is Ag. All right. So we already know that the metal should correspond with the metal ion. So if this metal ion is Ag, the metal would be Ag as well. So A is Ag if they ask us, right? So they said they also used copper. So this here should be copper, and the solution here should be a copper 2 plus solution if they do ask us. So how is this galvanic cell working? Remember we said that Cu is a better donator of electrons than Ag, right? So it means that Cu would donate its electrons. Those electrons would be accepted by Ag plus. So when Cu donates its electrons, the electrons would flow in that direction. Then more of the Cu2 plus would fall into the solution. Then this solution would become more positive, right? Because of Cu2 plus falling here. Then what does the salt bridge do to neutralize the positivity? The salt bridge would bring in negative ions. Then the opposite would be true. This side, the salt bridge would bring in positive ions. Then those electrons that were flowing in the outer circuit, when they get here, they get accepted by Ag plus. Ag plus accepts that electron. Ag plus, when it accepts an electron, it becomes Ag solid. So that Ag solid would then accumulate here and coat this, right? It will coat it like that because now this is a solid, right? So here we would observe an increase in mass. Here we would observe a decrease in mass. The opposite would be true again. So this one where we see it being coated, this is our cathode, this is our anode. Can you see how I put in information before I even go to the questions? Now let's go to the questions, right? Let's go to the questions. They say that write down the name or formula of electrode A. I can already see that electrode A is Ag. I get B is Cu, right? Cu2 plus, the Cu2 plus solution, right? But now they say we should write down the overall um, balanced equation for the cell reaction, right? So I'm gonna start by writing what? Yes.
Before you continue, how do you know it's Cu 2 plus and Cu and not Cu plus and Cu?
How do I know?
That there are almost now two of reactions for copper. There is Cu2 plus that makes Cu, and then there's Cu plus that makes Cu. So which one do you know to use?
There is Cu
Because
plus. There is Cu plus that makes Cu, and there's Cu2 plus that makes Cu. Normally we go with the one here Cu2 plus, right? But then in a case whereby, let's say, they in the half reaction they show you that here they Cu plus, it means that you're gonna go with this half reaction. But then if they don't show you, we normally go with the Cu2 plus. I think, yeah, that's standard. Like we always go with the Cu2 plus, unless if there's something that can explain it here. Yeah, we always tend to go with the one year Cu2 plus. Yeah, yeah. I don't know why though, but we always go with the one year Cu2 plus. Just like with water. With water, we always go with this one. Where is it? We always go with this one. But there are many waters on the table if you take a closer look. Yeah. There's also this water here, but we normally go with this one. I don't know the reasoning behind, but just know that, or okay, it is what it is, and we need to take it the way it is.
okay, sir.
Yeah. But if I get any more details as to why, I will let you know. Yeah? Okay, the net equation, remember we have to start by writing the oxidation half and the reduction half, right? So as you can see, I've already indicated this half reaction. On this side, what's happening here? We are having a copper changing to copper 2 plus, right? So plus 2 electrons, right? So I need to balance the electrons first. So I need to multiply this one by 2. 2 here, 2 there, 2 there. So the electrons will then cancel each other out. Then now let's add the equations for the net. So I would have that Cu plus 2Ag plus gives me a Cu2 plus plus 2Ag, right? So that's the net equation. Now let's move on to 8.4. The salt bridge contains potassium nitrate. I told you that this is the common salt bridge they use. Potassium nitrate solution. So basically in here, there are many potassiums and many NO3 minus, right? So write down the formula of the ion that will move into the silver ion solution. So that would move in here. Which one? Is it potassium or NO that would go here? Remember, we already said that the positives need to go here. So it's going to be potassium, right? So let's switch it and write it properly. So potassium should be the one going in there. Then NO3 minus should be the one that's going in here, right? So our answer for this one is potassium. Give a reason for your answer. So now here you need to explain, right? So you can be like, as the cell operates, right? This side, Ag plus accepts electrons. So usually they would say use a reaction to motivate your answer. So you would use the half reaction of the side, right, to motivate your answer as to why these ions in the salt bridge are going here. So basically, the idea is as the reaction takes place, Ag plus gains electrons to become Ag, right? So this decreases, or rather, this makes the solution in here to be less positive, right? So to neutralize it, the salt bridge sends positive ions. That's more detailed, guys. Right? So I can say that as the cell operates, Ag plus gains electrons, or I can say Ag plus is reduced to Ag, right? Then I can say this makes the electrolyte or the solution more negative, right? Due to losing the positives, right? Because of if this is reduced to that, it means that I'm losing the positives, so it makes it more negative. So to neutralize the negativity, the salt bridge sends positive ions, in this case, which are potassium ions, into the electrolyte. I don't know how the mark allocation will be, but this is how I would explain it. Is it making sense, guys? This is a question from 2023. Ne? So, singayivala, guys. Singayivala with multiple choice. You know how we always do it. Singayivala with multiple choice. So this is 2022. Let's take a look at 2022. Guys, it's always the same thing. It's always that a piece of metal is placed inside a container with some ions, right? They see that a redox reaction has taken place. Use the 4B table to explain the answer. Oh, but then I like how they brought this question. Look, they say that a piece of zinc is placed in a test tube containing acidified permanganate solution. So when you would see, but then this is a negative ion. How would it react with this? The trick is that they said that it's acidified. So it being acidified, it means that it has hydrogen, right? So basically it's HMnO4 minus. Oh, so the solution that they placed the zinc metal, it's HMnO4, right? So you already know, okay, my ion is hydrogen and my metal is Zn. So will Zn donate its electrons to hydrogen? That's the question. But then you see how they gave you the information. It's kind of tricky. But then once you notice the trick here, answering the question is just the same as how we normally do it. Do you guys get it?
Yes,
All right.
Yes,
Then you'd explain here using the relative strength of either oxidizing. Oh, here they said use oxidizing agents, right? Then here's a galvanic cell. Guys, I'm sure there is no galvanic cell that you would get wrong at this point. So look, here we have Mn, we have Ni, right? So our donators that are involved, it's Mn and Ni. So the strong one should win. We go to our 4B table to determine which one is stronger. So Mn, where's Mn? Mn is here. Where's Ni? Let's look for Ni. I give Ni is here. So as you can see, it makes Mn to be stronger than Ni, right? So this one would then donate electrons. So we know that Mn is the one that is actually donating, right? So this one is the one that is donating. So when it donates Mn, when it donates electrons, it becomes Mn2 plus 2 electrons. So the Mn that it produces, it falls into the solution. So the Mn2 plus, more Mn2 plus falling into the solution. Then we have electrons flowing up there. So when the electrons get here, they would be accepted by the Ni2 plus, right? So when the Ni2 plus accepts those electrons, what happens to it? It coats this one here, right? So here we would observe what? An increase in mass. The opposite would be true for this one. Here we would observe a decrease in mass. Then the reaction that takes place here would actually be Ni2 plus gaining those 2 electrons. So Ni2 plus gaining electrons, it becomes Ni. Yeah? Then what else will we observe here? So this is our salt bridge. So why they might want us to label it, it's our salt bridge. So salt bridge neutralizes the solutions, right? So as the cell operates, as you can see, this side we are losing positives as they are attached to that, so it becomes more negative, right? So the salt bridge needs to send positives this side and it needs to send negatives that side. You've put in enough information here. So the net cell notation, already the electrons are balanced, so the net cell notation would be Mn plus Ni2 plus, giving us Mn2 plus plus Ni. This is the net cell, right? So the side that we see an increase in mass, this is also called the cathode. This is the anode. Guys, put in information before you answer the questions. Write down the function of component Y. It's the salt bridge, maintains neutrality of the electrolytes. In which directions will electrons flow? Now you see here we are talking about the flow of electrons, not the flow of anions in the salt bridge, the flow of electrons. As you can see, we've already indicated that the electrons would flow from this side and they would go this side, right? So they would flow from Mn to Ni, right? So our answer would be this one. Calculate the EMF. I'm going to leave this one to you, right? Write down the balanced equation for the cell taking place. Here we already did it. Now, the concentration of Ni, look, the concentration, they increased the concentration of Ni, 2 plus. They increased this one. Which reaction will it favor? According to chemical equilibrium, I increase the a reactant. Will I favor the forward or the reverse reaction, guys?
Forward.
I will favor the
Forward.
forward reaction. By favoring the forward reaction, does my E cell increase or decrease?
It increases.
Increase.
Increases. They don't even want a reason. You get your free mark. Is a galvanic cell difficult, guys? Who here
Now
is
I can
still?
understand.
Yes. Hmm?
I'm saying now I feel confidence.
All right. Yeah, that's the main purpose of the session. I'm glad you are feeling more confident about it. Please go practice more questions. Then also go watch the 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 video, the other video on electrolytic cells, where I was teaching electrolytic cells. If you have time, watch those videos, practice more questions.